All right, let's get right into it. Welcome to this explainer. If you're an engineering diploma or B.Tech student grinding through digital electronics right now, you are absolutely in the right place. Consider this your ultimate exam-oriented power study session. Today, we're going to master two of the absolute most critical sequential circuits in digital logic design: registers and counters. Whether you're sweating over university finals, prepping for a tough viva, or just brushing up on gate basics, we've got you covered. We'll break down the theory, tackle the numericals step by step, and give you those crucial memory tricks to secure top marks. Okay, let's look at the game plan. We'll kick things off with an intro to registers, dive into shift registers, and then pivot to an intro to counters and their key types. After that, we'll do a head-to-head comparison of registers versus counters and wrap it all up with actual exam questions and real-world applications. So, Section 1, Introduction to Registers, the fundamental building blocks. Before we even touch complex data transfers, we've got to remember that both registers and counters rely on one super basic component, the flip-flop. And a flip-flop, it stores exactly one bit of data. But what happens when we need to store a whole word? Well, I love this analogy from Geeks for Geeks to help visualize it. They say registers are like the computer's quick access shelves. They keep important things nearby so the computer can grab them fast. It's brilliant. Think about your microprocessor crunching some heavy math. It absolutely does not want to keep fetching data from the main slow memory. It needs a temporary, lightning-fast storage space literally right next door to hold instructions and intermediate answers. And you guessed it, that's exactly what a register does. So, structurally speaking, what actually is it? Well, a register is simply a group of flip-flops driven by a common clock. It's that simple. If you have an n-bit register, you're using exactly n flip-flops to store n bits of binary info. Look at these 4 D-type flip-flops wired up together. Because they all share a common clock input, a single clock pulse triggers every single one of them at the exact same time. This lets them load or output their 4 bits of data simultaneously. Moving right along to Section 2, Shift Registers Explained, moving data step by step. Now, registers don't just sit there hoarding data. Their whole deal is moving it too. In your university exams, I can practically guarantee you'll see a short answer question asking you to list the types of shift registers. They're basically categorized by how data gets in and how it gets out. We've got SISO, which stands for serial in, serial out, meaning data trickles in 1 bit at a time and leaves 1 bit at a time. Then there's SIPO, or serial in, parallel out, where it enters bit by bit but gets read all at once. PISO is parallel in, serial out, and PIPO is parallel in, parallel out. Plus, we've got bidirectional registers that can shift left or right, and universal shift registers. Those universal ones are the ultimate multitaskers. They can shift left, shift right, and parallel load, the whole shebang. This brilliantly illustrates a basic 4-bit serial in, serial out shift register. Check out how the output of the first flip-flop is wired directly straight into the D input of the next one. With every single clock pulse, the data physically hops 1 step to the right. The serial input feeds the leftmost flip-flop, while your final output is grabbed from the rightmost flip-flop. Okay, let's break down a classic serial transfer numerical example. Say we want to copy data from register A, which is holding 1011, into register B, which starts with 0010. We wire the output of A into the input of B, and we also loop A's output back into its own input, so we don't accidentally lose our original data. Now watch what happens over 4 clock pulses as the data shifts. At T1, the rightmost one from register A slides right into the leftmost spot of register B. Fast forward after 4 complete clock pulses, and register B has perfectly caught that 1011 sequence. Meanwhile, register A has just circulated its own data around to keep its 1011. Setting up a step-by-step table exactly like this, that's exactly how you're going to want to structure your exam answers to secure those marks. All right, Section 3, Introduction to Counters, Sequencing, and Event Tracking. So let's shift gears here. We're moving from data storage over to data sequencing. By definition, a digital counter is a finite state machine that sequences through a predetermined set of states driven by a clock pulse. But the absolutely crucial concept to grasp here is the modulus, or mod. The modulus of a counter is just the total number of unique states in its counting sequence. That's it. For instance, if a counter counts from 0 to 9, well, that's 10 unique states, which makes it a mod 10 or a decade counter. Seriously, memorize this definition. It's a total staple for Viva exams and basic gate prep. Next up is Section 4, Key Types of Counters, Synchronous, Asynchronous, and Special Architectures. Pay close attention here, because this comparison is an incredibly common 5-mark question. In asynchronous or ripple counters, only the very first flip-flop actually gets the external clock pulse. The flip-flops after that, they're triggered by the output of the previous one. This creates this cascading ripple effect, which unfortunately introduces a propagation delay. On the flip side, we have synchronous counters. Here, every single flip-flop gets clocked simultaneously by one common clock signal. Since there's no waiting for a ripple to travel down the line, synchronous counters are way faster and more reliable, even if they're a bit trickier to design. Now, what's really interesting about this is how we can easily manipulate normal binary counters to count to whatever number we want. Think about it. A standard 3-bit counter naturally has 8 states, counting 0 to 7. But what if we just need a mod 6 counter, counting 0 to 5? Easy, we just use logic gates. By wiring the outputs that make up the binary number 6, which is 110, into a NAND gate, we can trigger the clear input on all the flip-flops the exact split second it hits 6. Bam! It instantly resets to 0, cutting the sequence short and giving us a perfect mod 6 counter. Before we wrap up our counter talk, I want to give you a quick cheat sheet for your multiple choice questions. If you're working with n flip-flops, what's your maximum number of states? Well, for a standard binary counter, it's 2 to the power of n. So 3 flip-flops, that's 8 states. But watch out, because for shift register-based counters, the math changes. A Johnson counter's modulus is just 2 times n, and a ring counter, it's literally just n. So here's your memory trick. Binary uses exponents, Johnson multiplies by 2, and ring is just n. Keep that tucked away, it will save you so much time on competitive exams. Moving to Section 5, Registers versus Counters, a head-to-head comparison. Now that we've seen how both of these work on their own, let's put them head-to-head. University examiners absolutely love asking you to contrast these two. At a fundamental level, registers are your data handlers. They're built for lightning-fast data storage and manipulation right inside the microprocessor. Their main drawback? Pretty limited storage capacity compared to your main memory. Counters, however, are your event trackers. They're built specifically to tally events, run timers, and do frequency division. But their architecture strictly boxes them into those timing and counting roles. You'd never try to store a complex instruction in a counter, right? To see why any of this actually matters outside the classroom, let's look at where they live in the real world. Registers are the beating heart of CPU and memory systems, juggling status flags and math operations. Shift registers are what makes serial data transfer between remote systems possible. And counters? They are doing the heavy lifting in almost every device you own. They handle frequency division and telecommunications. And honestly, if you glance at a digital clock, you are literally looking at decade counters ticking away the seconds and mod 6 counters wrapping up to 60 for the minutes. All right, final stretch. Section 6, Exam Questions and Applications. Test your knowledge. We've built up a solid foundation. Now, let's put that theory to the test with some questions pulled straight from standard digital logic textbooks and real Viva sessions. Picture this. You're sitting in your Viva exam, and the professor looks at you and asks, what is the primary function of a status register in a CPU? Take just a second. Do you have the answer? The key is that it holds specific flags. So while your general purpose registers are busy holding the actual numbers, the status register is holding single-bit flags, things like carry, 0, negative, and overflow. These little flags tell the CPU the result of the very last mathematical operation it did. Pro tip, if you want to seriously impress your examiner, mention a real-world example like the current program status register or CPSR in ARM architecture. They love that kind of detail. Okay, let's tackle a classic written textbook problem. Problem 6.4 goes like this. A 4-bit register initially holds 1011. It is shifted 6 times to the right with a serial input of 101101. What are the contents after each shift? So here's exactly how you want to lay out your answer to get full credit. Step 1, write down your starting point, your initial state, which is 1011. Now keep in mind we are shifting to the right. That means the rightmost bit is going to fall off the edge and disappear, and our brand new serial input is going to slide in from the left. Okay, step 2, the first shift. The very first bit of our new input is a 1. So that 1 enters from the left, pushes everything else to the right, and that old rightmost 1 drops off. We're now left with 1101. Step 3, the second shift. Our next input bit is 0. The 0 slides in from the left, shifting everything right again. Our new state, 0110. Step 4, the third shift. Next input bit is a 1. The 1 enters from the left, shift it all right, and we land on 1011. You just keep following this exact logical progression for all 6 bits. Writing it out clearly, step by step like this, shows the examiner exactly what you're doing and pretty much guarantees full marks. Let's do a super quick recap of your major takeaways from this explainer before your exams. Registers, they use N flip-flops for rapid-fire data storage and movement. Counters, those are your sequential state machines for tallying up events and keeping time. Remember to nail down those mod formulas. Binary is 2 to the power of n, Johnson is 2 times n, and ring is simply n. And finally, don't forget the core architecture difference. Synchronous counters use one simultaneous clock for speed, while asynchronous counters rely on that cascading ripple effect. Now, I want to leave you with a bit of a provocative thought to chew on during your next study session. We just saw how adding a tiny handful of flip-flops can exponentially blow up a binary counter's capacity. So mathematically speaking, it seems infinite, right? But what physical hardware limits? Things like propagation delay, thermal heat, or literally just running out of space on a silicon chip prevent engineers from building infinite mod counters in modern microprocessors. It's wild to think about how the physical laws of electronics put a hard stop on our logical designs. Think on that one. Thanks so much for learning with me today. Keep practicing those numericals and absolutely crush those exams.